stuff like that.
Yeah, I noticed your red black slides, they don't mention tree maps at all, and they don't mention runtimes.
Okay, yeah, well, because like they don't yet. Mostly I was just trying to figure out like what version are we gonna do, and actually the slides are probably like a little off, like misleading right now, because I was like, oh, maybe I'll do red black trees and then we'll do left leaning, and I was like, no, I think we're gonna do 2, 3 like trees and then transform them to left leaning red black trees.
That's what Kevin does.
Yeah, it's the canonic way to sort of teach it.
All right.
Anyway, so yeah, okay, then I think I could probably at least come for the first bit, and we could talk through that.
Yeah, and then I already looked at how the grade school assignment would work.
Oh yeah,
it's really seamless. Yeah,
fabulous.
I already uploaded like a draft copy PDF or whatever. You can already make the outline. You can already do the rubric. Yeah.
Okay. Great, then then after this, I will come with you. I'll stay at least for I think the first 30 minutes. I think I'm gonna be 30 minutes late to this next thing.
Sure.
I think so, because like I think my next meeting's for like an hour. So
and honestly, at this point, I think it's just me and Simon, because I think everyone else is like, no,
busy.
I'm dying. Like,
yeah, fair.
But yeah.
Okay, hopefully a shorter warm-up, but put your brains back in the tree territory. I know we did it for all of like 7 minutes at the end of lecture on Friday, but welcome to Trees Week. So take a look at this structure and answer yes or no to each of the questions. Is it a binary tree? Does it satisfy the BST invariant? Is it balanced? You may not know what all of those words mean. That's okay. We're going to dig into it in more detail today. But at least chat through it, the people around you. The Slido should be open. Let's come back together in like 2 minutes. I think this one's on the shorter side. Go ahead. And also, I'm pretty sure Robbie is the originator of that nested latex situation that's going on, and I would love to hear his thoughts on what's going on in there. Because until you came and talked to me, I was like, oh my god, Sherdill's just been doing it in the background, and I didn't know. Yeah, so sounds good. If you haven't taken some guesses on the Slido, now is your time. We're going to chat about this sooner rather than later. I like all the gesturing that's happening because we're going to get real geometric this week. All right, let's see what's going on the Slido. And theoretically, I was smart enough. Okay. Ooh, look at this. We've already got 115 votes. We're on top of it. Hang on, let me change. No, that is half on. I keep looking at the screen thinking there's a better lighting for it. I'm sorry it's in such dark colors. Okay, let's see what we've guessed. Okay, so we've got 3 separate questions, each of which may or may not be true about this binary tree. These questions we are going to now refer to as invariants. That's just the fancy word for things that are true about our data structure. At the end of last lecture, for those who took 143, met, and for those who took 123, reviewed the binary search tree. The binary search tree is a tree with a certain set of requirements. It must meet those requirements in order to be defined as a binary search tree. So the first requirement is that it is a binary tree. Does anybody happen to remember the definition of a binary tree? This is just straight up like, do you remember this thing I said at the end of last lecture? Yeah, over there. Yes, perfect. Every node has at most 2 other nodes. We usually refer to those other nodes as children. We often refer to them as the left and right in the binary tree scenario. I say this because up until now you've probably only met binary trees, but the bi in binary does mean 2. And there exist all types of trees, trinary trees, ternary trees, n-ary trees. But in this particular context, it is a binary tree, which means every node must have at most 2 children, but it can have 0 children. That would make it a leaf. So I agree with 97% of you. Yes, our example was a binary tree. The second one, is it balanced? Okay, it was in the slides, and I straight up was like, no, I'm not going to talk about this. And then I asked you this question, mostly because it was based on the assumption that I actually did do that slide. We're going to do that slide for real today. But I thought it would be interesting for y'all to sort of discuss it anyway. So I asked, is it balanced? And 63% of you said yes. Does anybody want to tell me why they maybe said yes? It is totally okay. We did not actually go over this. I'm just sort of curious what your thoughts were when you were looking at that tree. What made it look balanced to you? Yeah. Yes, please. Very, very close. Thank you for looking ahead. Just brownie points. Not that I expect all of you to do that. But we're going to get into the formal definition of balanced. But if we go back over and we kind of look at our tree here, we can see that, like, I was kind of expecting somebody to be like, it kind of looks balanced. Like, it kind of, in my gut, feels balanced. There is a mathematical way to determine this. But if you look at it, there is no one particular path from the root down that is exceptionally longer than any other path. We will give it a formal definition where we will say no path can exceed any other path by more than 1. And so this does meet the definition of balanced. So I agree with the 67% of you that I assume went by your gut. Now, the one that I do think we talked about is this middle one, the BST invariant. Did I put it there in those particular words just to mess with you? Yes, I did. So remember that binary search tree? We abbreviate it as BST. So BST stands for binary search tree. The invariant is just that fancy word for does it satisfy these rules? Can anyone remind us the binary search invariant? What must be true about the ordering of the values for it to be a binary search tree? Yeah, in the back. Yes, perfect. Our left children are always less than the root, and our right children are always greater than the root. So, does this tree satisfy the binary search invariant? Ooh, I see some head shaking. If it doesn't, can anyone raise their hand and tell me maybe which node breaks the binary search invariant? Yeah.
The 12 that's coming after the 10 will be
The 12 right here. So because this 12 is to the left of 10, according to our binary search requirements, anything to the left of 10 must be less than 10, but 12 is greater than 10, so you're absolutely right. This breaks the invariant is how we would say it. But if we look at the other nodes, right, like we see 6 here is our overall root, 3 is less than 6, cool. And then we see all of these nodes here are also all less than 6. The rule applies recursively. And so that's all good. And we look to the right here, we notice this whole set of nodes is greater than 6. That's cool. And we look to this 8, 7 is less than 8. But 10, 11, and 12 are all greater than 8. That's fine. It's just we sort of swapped these left and right children here, or not really swapped them, because really the 12 just needs to be over here to the right. Now I will tell you, if we had picked up that 12 and actually put it over to the right so that it was sticking out to the right of the 11, we would have satisfied the binary search property, but we would have broken the balance property. And in fact, that is all we are going to be talking about today. Breaking an invariant and then fixing it, satisfying one and then satisfying the other. In fact, this whole week is all about how we break and then satisfy these types of invariants to maintain a tree in a particular organization that is optimally structured for what we're trying to do. Does anyone have any questions about this practice problem? Cool. Okay. Yes, thank you. Animations. Okay. Okay, reminders. Exercise 2 is due this evening by 11:59. That means that exercise 3 is all about trees. It will release this evening. And then, of course, your project 2 is out. It's not due Wednesday. It's due the following Wednesday. Does anyone have any course administrative questions? When is your first exam, somebody? Yeah, a week from Friday. I also heard somebody say it. Is it the 27th? 28th? Yes. Not this week, but next week. You've got time, but I'm reminding you. Okay? We're going to talk about it more later. Okay. So let's talk a little bit more about these binary search trees. So this is sort of where we left off on Friday, where we have these two types of trees. And the thing that's really great about the binary search property is that it gives us this sort of directed way to move through the tree so that we know exactly where to find the thing we're looking for. And by each sort of decision, left or right, we eliminate some number of nodes we have to look at. If I was calling containsKey on these two different trees, first I will ask, is the tree on the left a binary search tree? It was like a slow roar of then shakes. Yeah, this is not a binary search tree. On the left-hand side, you can see right away that 9 is to the right of 32, and 9 is definitely not greater than 32, and there's a bunch of other ones in there. So the tree on the left is definitely not a binary search tree, though it is a binary tree. The tree on the right-hand side, is that a binary search tree? Yes. I think you anticipated my question because the nods came quite fast that time. Yes, the one on the right-hand side is a binary search tree. So if I was looking for the value 2, in the non-binary search tree, just the regular binary tree, I have no idea where the 2 is going to show up. So I literally just recurse left and right until I find the thing I'm looking for. I should have actually put a green around this 2, and then I would have returned. But it's like, you end up with sort of an N traversal. It's almost like a linear search because you just don't know where that thing's going to be. But once we have things ordered, we can run that binary search property. And at the 10, we can say, hey, 2, are you less than or greater than? Boom, less than. So I can go to the left. I can cut this way. And I know I'm never going to have to look at any of these nodes over here to find the thing I'm looking for. We come to the 8, and we're like, hey, are you less than or greater than? Less than. So I can go to the left. And I never have to look at this 9. So we get a much more efficient lookup time in the binary search property. Great. How convenient for us. Here's some code if you are compelled. So here is just the sort of equivalent of linear search, but in the binary tree world, where you can see, hey, if the node's null, that's not what I'm looking for. If the node is what I'm looking for, great, return. But otherwise, just go left, go right. You can see I have a logical OR here, so if I find it, I like sort of stop where I'm at. But otherwise, it means just like look at everything in the tree. Versus, if we come over here, look, it's almost, gosh darn, the exact same bit of code, except you can see we only do one recursive call, either or recursive call instead of sometimes both. That makes a huge difference in the performance. That's a whole coefficient in our recurrence. So let's talk about runtime. Okay, so here is a recurrence of what we might write here. If I was to write a recurrence for this piece of code on this tree, well, I've got this 3 that's like, I don't know, like maybe that's like this check and then like this check and then a return. I don't know. It's some constant number, right? Otherwise. And then we can see here, we've got this one recursive call. See, there's no coefficient in front of that t, because we know we're just going to make one recursive call. We've got some amount of, like +1, like maybe that's this check here kind of thing. And then we have this n over 2. Where do we think that n over 2 comes from? What is that telling us about the way we're modeling this code? Any thoughts on that? Yeah.
You're checking one or the other, so it's like there's 2 options.
Yes, exactly. There's 2 options at each fork in the road, and I'm picking only one. But this n over 2 means that I am sort of assuming that when I pick one direction, that I am leaving behind properly half of the possibilities. And so this means at each level, I'm eliminating half of the possibilities, just like the binary search algorithm that we learned previously. Like in my little dictionary example, we open up to the middle of the dictionary, we go left or right, then we throw away that half of the dictionary that we don't need anymore. We eliminate and we eliminate. This ends up giving us logarithmic runtime, if you remember, and gosh darn it, logarithmic runtime is way more efficient than linear runtime. But this is making an assumption. Can you imagine an orientation of a tree in which we are not able to put n over 2 in that recurrence? Can we always assume n over 2 in this binary search situation? What might a tree look like that we could not put n over 2 in that spot? Yeah, all the way in the back. Aha, that sneaky degenerate list. It sneaks in so many places. And yes, the worst case scenario is if this binary search tree actually was just a, what we call officially degenerate tree, where it was just essentially a linked list, like it was like all right children or all left children. And actually that could totally happen because, say, for example, you inserted everything in ascending order or descending order, which could totally happen. You could end up with just a really, really, really imbalanced tree. In fact, there we go. This is what that tree might look like. So for example, this tree is what would result if I inserted the values 1 through 15 in that order. If I put 1 into the tree, it would become overall root. If I put 2 in the tree, it would go to the right of 1. If I put 3 in the tree, it would go to the right of 2, blah, blah, blah. So on and so forth. So it's not really, oh, I need to replace this. It's not really n over 2 here. Ignore that. Does anybody want to tell me what's actually should be on my slide? What's the correct, how would we model this? If it was actually the degenerate tree, how many possibilities am I necessarily eliminating each time I go one level deeper into the tree? Instead of dividing n in half, how am I reducing n? Yeah? Yeah, in the middle. N minus 1, exactly. And it's like the one I just dealt with. So t of n over 2 gives us logarithmic time, but t of n minus 1, ignore this, imagine this says n minus 1 here, that actually, if you plug and chug it into like our unrolling method or our tree method, and you close form all the summations and do all that stuff, you actually end up with linear time. Because it's really not reducing my possibilities at each sort of fence post as much as I would like it to. Any questions on that? That's sort of a core idea behind the crazy trees I'm now going to subject you to. Okay, so it's really nice to have that search property. That search property really benefits us most if at each sort of level of the tree we eliminate half of the things. Also, if you can't tell, there is something about the height of the tree that becomes very important. If it's just that linked list, we have a very tall, skinny tree. And remember that the way we move down a level in the tree is to make a recursive call. And in this sort of situation, like if you're thinking about it in relation to iteration, each level down is like another time you got to go over and do your code again. It's like another iteration. It's another level deeper. So the taller and skinnier your tree is, the more recursive calls you need to make to get all the way down to the bottom of it, versus the bushier, the fuller your tree is, the shorter it will be, and it will take fewer recursive calls to get down to the bottom. So your sort of repetition will happen fewer times. You will get better performant code. So, wouldn't it be amazing if we created a tree that forced itself to stay nice and bushy and short? We shall add some invariants. Oh yes, thank you, Hunter, for animating that. We're going to add some more rules to our structure and see if we can force this tree to be a little bit better behaved. We're trying to avoid that degenerate situation happening. So we're looking for a short BST. What's one thing we could do? What if we were like, oh, well, we know that a totally full tree will have a height of log n. In fact, if it's a binary tree, it'll be log base 2 of n. If it's a trinary tree, it'll log base 3 of n, so on and so forth. So we know the height of the tree is the distance I have to travel in recursive calls. That's logarithmic. So maybe I could like put some type of like, hey, you can't get any taller than this. This is technically what we want, but it is so difficult to code a tree that just checks its own height and then like forces itself to be squat. That's our goal, but that's not really going to help us in implementation. So instead of sort of like thinking of the final end goal, we're going to pick an invariant that sort of always maintains a positive state. It's like we don't want to get too far degenerated because it's always harder to clean up a bigger mess than to just wash that dish as soon as you dirty it, says my partner, and I never listen, right? So instead, we're not going to like force it to be perfect at the very end. We're going to think about at every stage, what's the moment that I break an invariant and how do I immediately correct it? So that's one thing. The other thing too is that it's actually really hard to force the tree to be perfectly log n or to be perfectly balanced because it's based on like, you know, as we add things in, we might have an, you know, uneven amount of things in the tree. We need a little bit of wiggle room that keeps us roughly within the good runtime, but still allows for sort of the natural order of as we build up the tree. So, all right, that's doing the most. Okay, so meet the AVL invariant. What we're actually going to do, and this is the definition then of balanced, is for every node, the height of its left and right subtrees may only differ by at most 1. So you see how it says at every node, this is a recursive invariant. So if we think of it in terms of like starting small, as long as we apply this at every single node, no matter how big our tree gets, it'll kind of maintain this balance. And I'm going to show you exactly how we do that. But that's the goal right now, is we've added on a sort of fourth little rule about our structure. So welcome to AVL trees. These are the most probably, I'm going to say famous, of the self-balancing trees. They are probably the most likely to be referenced in an interview or in some other scenario. We are going to spend an entire lecture on them today, and I'm going to give you sort of like a flash of a bunch of them on Wednesday. But if you learn one type of self-balancing tree, this is probably the one. Okay, so it's named after, I don't know, some white dudes. Sorry. Say la vie. What? There's one? Yeah, maybe we'll double check. If there's a lady, I will eat my words. But it's just, yeah, so AVL stands for their last names. That's where that comes from. And so what we're going to have is if we maintain this type of balance at each individual node, that sort of means that the whole tree is going to have a balance to it, which means the tree's height will be log n, which gives us a worst case guaranteed runtime of log n. The way that we are going to implement this AVL tree is not like the hash table. Remember the hash table? We were kind of doing everything we could to like hedge our bets, that we didn't end up with that degenerate situation, but there was technically no forcing, right? Like there could have still been n collisions. It would just be statistically very unlikely, but there was no real forcing function from that happening. In this situation, we are going to actually write code that makes sure that we never get that weird linked list sort of tree situation. So, AVL trees, they must be binary trees. They must be binary search trees. And they must be balanced. So, that tree we had for warm-up, it was a binary tree and it was balanced, but it wasn't a BST, so it's not an AVL. But if it was all three of those, it would have been a valid AVL. So, how do we measure balance? We compare the heights of two subtrees. So, okay, I was going to say, I think I didn't separate the animations. So let's start here with this tree. We've got an 8. It's got a 7 to its left and a 9 to its right. Is it a binary tree? Is it a binary search tree? Yeah. Is it balanced? Yes, I agree. This is sort of the core little relationship of a balanced node here. Let's look at this second one here. So we've got 10 as the overall root. 2 10s left, it has a tree of height -1. To its right, it's got a tree of height 1. I know that might feel weird, but we use the null, like there's no tree here, to have a height of -1. And then we count the heights based on how many sort of levels are between the two nodes. So the subtree connected to the right of 10, meaning if we start at 15 and we include the 12 and the 18, this little grouping of 3 here, we count that to have a height of 1. So if I have a left subtree of height -1 and a right subtree of height 1, is it balanced? No. This is not an AVL tree. This is an imbalanced tree. The right subtree is just a little too long compared to the left subtree. If instead I had one node sticking off of the left of 10, then it would be balanced, because then it would have a tree of height 0 to the left, one node all by itself, and then a tree of height 1, which is the 3 nodes, and the difference between 0 and 1 is still 1, and we allow for a difference of up to 1. So it doesn't have to be perfectly balanced, just a difference of at most 1. Let's look at this 8 and the 7. So 8's left subtree is the 7, and its right subtree is null. Is this balanced? Yes. If it helps again, To the left, we think of this 7, just the node by itself, as having a height of 0. If it helps, I think of it as like an acorn or like a bulb in the ground. Like, it doesn't have any branches, so it doesn't have any height, you know? And then we've got this null, nothing exists there, it's -1. But the difference between 0 and -1 is 1, so it is still balanced. What about this 7 just hanging out all by itself? Is that a balanced tree? Yes. Its left and right children are exactly the same. They're both -1. So that's how we calculate balance. Does anyone have any questions? I know the -1 height thing is a little weird. We'll get practice. Yes?
So when we measure height, do we start from the first child of this? Like start from there and it goes down this one, goes like this thing?
Yes, you start from the children. So I think of what's the height, not counting from me down, but like comparing the height of my left child and my right child, starting at sort of like the top of them, if that makes sense. So I'm not comparing the height of 8 to 7 is 1, 8 to 9 is 1. I'm comparing, hey, what's the height of 7? It's a node by itself. What's the height of 9? It's a node by itself. These are two subtrees of height 0. Combined with the tree of 8, they have a height of 1. That 3 combination has a height of 1. But the two nodes by themselves, that's what we're comparing to know if my left and right children are in balance with each other. Yes?
And in the unbalanced case,
Yes.
if you remove 12,
Mm-hmm.
would the height of 15 still be 1?
If you removed 12, would the height of 15 still be 1? What a good question. What are our instincts? What do we think? Yes. Because even though it doesn't have 2 children, as long as there exists one path, you determine height based on the longest path. So this is also a good observation. A line of 3 nodes down one direction is an imbalanced tree. In fact, that is one of the core imbalance cases. Let's get into it. Okay, for your homework, is this a valid AVL tree? Go ahead, talk to each other for a minute or two. Answer these questions. It's 2 Soviet dudes. I'm not surprised. Ah, you're right. It's two humans, 3 names. Yes. Oh my gosh. Like, yeah, like, is it a BST tree? Yeah. Oh, yeah, you're right. Yeah, you're right. But it would sound weird to say a BST tree. That's wrong. But ATM machine, I stand by. Just like it will forever be GIF. I don't care if the founder says it's GIF. He's wrong. All right, in the interest of time, let's start with the first question. Is this a binary tree? Thumbs up or thumbs down? I agree, thumbs up. Okay, does it satisfy the binary search property? Thumbs up or thumbs down? Ooh, we see some thumbs up. Okay, all right, I think the thumbs ups have it. Okay, is it balanced? Thumbs up or thumbs down? Aha, we see thumbs up. Okay, great. Does anybody have any nodes that we want to like investigate? What are some suspicious nodes? Let's see. Maybe that 14 looks kind of suspicious. It feels like it's maybe like sticking out a little further than it should. But if we're ever suspicious, we can go investigate. We can see, okay, I start at 14 and I go, okay, is 13 imbalanced? Well, it's got a -1 height and a 0 height. That's fine. So I'm going to recursively go up. I'm going to say 12. It's got a height of 1 versus a height of 0. Ah, that's balanced. Okay, great. And then I go up and I say 10. It's got a height of 1 versus a height of 2. Okay, that's balanced. Then I go up to 7, and it's got a height of 2 compared to a height of 3. That is also okay. That is balanced. Any questions about how we got there? Yes?
If, in the case of like the left branch, you can see how it's 4, 5, 6. If the 6 was missing, would it still be considered balanced?
Ooh, good question. Okay, let's see. So if the 6 was missing, that would change this subtree from a height of 1 to a height of 0. This subtree here is a height of 1. So right now, 4's left and right children both have a height of 1, but if we got rid of the 6, we would have a 1 and a 0. It'd still be balanced.
And it doesn't matter about the right side?
Aha! Doesn't matter about the right side. So if that was the case, if we got rid of the 6, we kind of go up, we decided that the 4 would still be balanced. Well, 7 would have a left child whose maximum height would still be 2. And we would still compare that to the maximum height of 3. Because even if we got rid of the 6, this would be the longest path on the 4 subtree. So 4 would not actually lose height by losing that 6, because it's still got the 2 hanging off there. Yeah. Great questions. Yeah? What if we got rid of the 8? Yes, let's see. Okay, so if we got rid of the 8, the 9 would be okay. And then we go up to 10, and we would compare 10's left child, which would be just the 9, so a height of 0, to its 12, 11, 13, 4, which has a height of 2. So 0 and 2, would that be a balanced node anymore? No. So yes, if we eliminated this 8, that would imbalance at the 10. Great. There's more, but in the interest of time, I'm just going to leave this in here for you. This is just for your homework. I promised you I'd do a problem. Okay. So hopefully now we know what a valid AVL should look like. How do we force it into that delightful shape? So we know we've got this invariant. We know also in our code when we are going to break that invariant. Anytime we alter the structure of the tree, there's a chance we could break the balance invariant. So what we are going to do is we are going to track the heights of the subtrees, and then we are going to detect the imbalance, and we're going to restore the imbalance. What this also means is that I am going to place the nodes initially based on the binary search property. So I am going to always follow the binary search property. Like this node's going to go wherever the binary search dictates it must go. But once I place it where it must go in the tree, I will then ask myself, have I now broken the balance? And then I will fix the balance. So I maintain the binary search. I'm going to fix the balance. This is going to be a common pattern for us where we have multiple invariants like this, and there will be one that is easier to maintain and one that is easier to fix. In this case, easier to maintain the binary search and to fix a broken imbalance. How do we do this? Welcome to AVL rotations. Once upon a time, Mean Casey made you draw all of these out on your midterm, and it was a disaster. And the poor TAs had to do this whole, like, is it double jeopardy if they mess up, like the subtree kind of thing. I am no longer going to ask you to draw out the AVLs on an exam. You will have to do it on your exercise, I believe. You have to know what's going on there. But I'm not going to ask you to sort of draw out the AVL in the exam, but I am going to ask that you understand what's happening underneath and the implications to the runtime. So, insertion. We know that's a moment where we could accidentally imbalance our tree. So, I've got a tree right now of just 1 and 2. Is this a valid AVL tree? Yes. These 2 nodes are happy little neighbors. They are balanced. Is this a valid AVL tree? No, because one's right subtree has a height of 1 and one's left subtree has a height of -1. That is more than a 1 difference. So we are going to do this rotation where we know where things can kind of go based on the binary search property, but it's going to sort of redistribute the height. The AVL will rebalance. So we are going to be changing a bunch of pointers around. Surprise. Okay. This sort of act of identifying when the balance is broken and then sort of configuring oneself, that's the definition of a, quote, self-balancing tree. And that's really what we're talking about today. We're going to be talking about it all day Wednesday, is this whole category of trees, because you will find, again, the search property is easy to maintain, but there's a million different design ways to fix an imbalance. So I'm going to show you one way to fix an imbalance, and on Wednesday I'm going to show you a bunch more ways to fix imbalances, sort of like in hashing, where like collisions had a lot of different ways we could design out of. The self-balancing and imbalanced tree, that's another area where there's a lot of different design decisions, some and better for some situations. Okay, so here is a tree. You can see the little heights there. So we've got 1, 5, and 8. Is this a valid AVL tree? No. I like to think of it as I sort of like grab that node in the middle and I sort of like pull it up. And by pulling it up, it sort of like forces the other one down and it sort of rebalances the line. That's what my little hand animation is doing there. This is what's called, in this particular case, a left rotation, because it was sort of like the line was pointing to the right, so I needed to sort of pull that middle one up and force that top node down to the left. So I sort of had to move the tree in the opposite direction that it was sort of leaning towards, right? Because if I want to balance something, I have to counteract the direction in which it's leaning. So if it's leaning right, I got to rotate left. This is called a left rotation. You apply whenever a newly inserted node is located under the right child of the right child. Here is a more accurate and specific. What you can see here, and I know this is kind of hard to read if you're not familiar with this type of notation, is these little triangles here represent whatever comes in the tree after these nodes. Because remember, this can apply recursively. So it was hopefully a little more direct to see it when those 3 nodes were just those 3. But this could happen where each of those nodes could have their own children. But because of the binary search property, I actually am guaranteed that I can redistribute these children and still maintain the search property. So, because I know that B must be greater than A, because that's where it originally was, I know that everything to the left of B is less than B, but I know that it will be greater than A. So when I rebalance, what I'm going to do is I'm going to swap B's left child, instead of pointing to whatever the heck it was holding before, now it's going to point to A. But because I did that, I need to find a place for that thing I was previously holding. But because of the binary search property, I know that everything that was to the left of B can go immediately to the right of A and still maintain that search property. And if you can see, none of the other subtrees changed. So what I really just did here is I swapped B's left child to point to A, and A's right child, which was previously pointing to B, now points to B's left child. I just swapped this arrow right here with this arrow. And that can then apply recursively to however many nodes are hanging out under there. More examples. Okay, guess what? There's a right-hand rotation. So if we had 3 nodes leaning to the left, again, if it's leaning to the left, I got to rotate it to the right. I'm going to do the same sort of thing where I'm going to take that one in the middle, and I'm going to swap A's left child to point to B's right child, and I'm going to point B's right child to instead point to A. And because of the binary search property, I'm guaranteed to know that that will still work according to the BST property. Does anyone have any questions on this particular rotation? Yeah?
We just are checking every single time we insert a node to see if the heights are like too far imbalanced to do this?
Yes, exactly. And thank you, I maybe didn't say it clear enough. The way that we are checking the heights is, do you see how I have this little h equals 2, h equals 1, h equals 0 here? That's going to be a field in each of these nodes. And every time you add a child, you sort of increase that sort of height there. And so then you can always compare the heights. If you recognize your heights are imbalanced, there you go. See, like previous, that was a height of 2. I moved it down, got rid of its children. I updated its height. So I have this field called height that I am checking, and that's what lets me know I can do this type of rotation. I've hit an imbalance. So I'm maintaining the field height as I go. I'm checking it at every insertion. I'm checking it at the insertion of that specific node, and I am checking it as I recurse back up, because this has to apply recursively. Yes?
What is the value in the subtree? The 1, 2, 3, what are those?
Which one, sorry?
1, 2, 3, like what are those
Oh,
values?
so those values, okay, this is the annoying thing about this notation. They're numbers here so that you know that I'm just numbering the subtrees. Those are not actually values inserted into the tree along with letters, but that is confusing. So this is just whatever the heck is to the left of C, that's subtree 1. Whatever the heck is to the right of C, that's subtree 2. But I know that whatever happens to be in subtree number 3 here, I know it has to be like greater than B but less than A because of the place it's in, which means the other valid place it could be is to the left of A. It gets more complicated. Yay! Okay, so we've got our happy little balanced AVL here. The 1 and the 3 are so happy. Is this a valid AVL tree? No. We've still got that sort of imbalance, like 1's left subchild has a height of -1 and its right child has a height of 1. But like, if we want to do a rotation, it doesn't like really help. So what we have to do is we actually, in this particular case, we have to do a double rotation. So previously you saw what we refer to as the line case, when you have, like your imbalance happening all to one extreme. This is where the imbalance happens in one direction and then again in the other. So a single rotation will not resolve this. You must do a double rotation. So what you do in this particular case is you rotate the bottom part of the tree to get to the line case, and then you do the line rotation. And that will always be in opposite direction. So what happened here is we rotated 2 and 3 to the right. So I got 1, 2, 3. Now I rotated 2 to the left to get a balanced tree. So here we go. You can see, there we go. I've got, yes. So right, left rotation, this is just lots of slides for you. So here you can see, right, like I couldn't just sort of like invert these things, but I can rotate this bottom half to get to the line case, and then I can rotate to get my nice happy little pyramid shape there to get a perfectly balanced tree. Here you can see all of that notation. Technically the BST properties still apply, because what I'm going to eventually end up with is C's 2 subchildren. They are going to get reassigned, where to the left of C will go to the right of A, right? Because it's right 1 and then all the way to the left. And then B's left child, that will be 1 to the left of B and then all the way to the right. And that frees up C to point to A and B. You can see more of this. Okay. I am going to click through this example, which is exactly how far I plan to get today. So let's say we have an 8, we've added a 9, we've added a 10, we are imbalanced. We are imbalanced at the 8, we're going to rotate, great. We have a balanced tree, 1 rotation. I am now going to add in the 12. Is this imbalanced? No. I'm going to add in an 11. Is this imbalanced? Yes. So I'm imbalanced at the 10. I'm going to rotate, and then I'm going to rotate again, and I have a balanced tree. So these are the 4 AVL cases technically, the 2 line cases, the 2 kink cases. One triggers a single rotation, one triggers a double rotation. The rotations are actually consistent across self-balancing trees, but all that pointer changing, I hope it terrifies you, because it should, because it is such a hard thing to implement. I'm literally not going to ask you to implement this code. But come back on Wednesday, I'm going to show you a self-balancing tree that actually is so clever, you can implement it no problem. All right, see you on Wednesday, y'all. Sorry, I didn't have a chance to get to the questions.
Oh, yeah. Because you guys have to actually implement it. And verify, okay. That makes sense. Sure.
So like if you have a tree that has like, so you have a root node and you have all the right, and it wouldn't have
I mean, I guess it depends on how tall that tree is. If you're saying like it is literally an overall root with a bunch to the left and a bunch to the right, you're right, that's not logarithmic time, because what's going to happen is after your first left or right, you will eliminate half, but then after that you just eliminate one. Yeah. So that's why it has to recursively apply at every node. Yeah, for sure. Yeah, you too. Hi. Oh, thank you. Oh, that was just